In the year 1957, a survey of the northern sky was underway at the Bologna Observatory in Italy, part of a broader effort to catalogue radio sources that had been detected at relatively low frequencies. The catalogue that emerged from this work was known as the Tonantzintla catalogue, named after the Mexican observatory that participated in subsequent optical identification efforts, and it assigned numerical designations to objects that had been cross-referenced between radio observations and photographic plates. Entry number 618 in that catalogue corresponded to a faint point of light in the constellation Canis Venatici, the hunting dogs, a region of the sky that contains no particularly notable naked-eye stars but sits in a direction that looks outward from the plane of the Milky Way into deep extragalactic space. At the time, the object attracted no special attention. It was one of many faint sources that appeared stellar on photographic plates but emitted radio waves, a combination that was only beginning to be understood. It would take decades of accumulating evidence, increasingly sophisticated instrumentation, and substantial revisions to theoretical astrophysics before the true nature of TON 618 would come into focus, and when it did, it presented the scientific community with an object so extreme in its properties that it challenged existing models of how matter assembles and grows in the centres of galaxies. To appreciate what makes TON 618 significant, it is necessary to trace the development of several ideas simultaneously. The recognition that some astronomical objects are vastly more distant and luminous than they first appeared, the theoretical framework that connects extreme luminosity to the accretion of matter onto compact objects, and the observational techniques that allow astronomers to estimate the masses of objects they cannot directly see. Each of these threads has its own history, its own sequence of debates and surprises, and they converge on TON 618 in a way that illuminates not only the object itself, but the broader processes by which supermassive black holes form and grow in the universe. The story of quasars, the class of objects to which TON 618 belongs, begins in earnest in the late 1950s and early 1960s. Radio astronomy had revealed hundreds of sources across the sky, and the challenge was to identify these sources with objects visible in optical telescopes. Many turned out to be nearby galaxies or supernova remnants within the Milky Way, but a subset of them appeared to be point-like, resembling stars on photographic plates. The term quasi-stellar radio source, later shortened to quasar, was coined to describe these objects, and the critical breakthrough came in 1963, when the Dutch-American astronomer Martin Schmidt examined the optical spectrum of the quasar 3 C273, and realized that its spectral lines, which had seemed unrecognizable, were in fact the familiar hydrogen emission lines, shifted enormously to longer wavelengths. This redshift, when interpreted through the framework of Hubble's law relating redshift to distance, implied that 3C273 was not a nearby star, but an extraordinarily distant object, billions of light-years away, and therefore extraordinarily luminous, far more luminous than any known galaxy. This discovery triggered an immediate and contentious debate. If quasars were truly at cosmological distances, their apparent brightnesses implied luminosities that exceeded entire galaxies by factors of 100 or more, all concentrated in a region small enough to appear point-like. Some astronomers, notably Hult and Arp, argue that the redshifts might not be cosmological, that some unknown physical mechanism could produce large redshifts without requiring enormous distances. This debate persisted through the 1960s and into the 1970s, but the weight of evidence gradually and decisively favoured the cosmological interpretation. Quasars were indeed distant, and their luminosities were indeed extreme, which meant that something in the centres of galaxies was capable of producing energy at rates that dwarfed thermonuclear fusion in stars by many orders of magnitude. The theoretical mechanism that could account for such prodigious energy output had actually been proposed before quasars were discovered, though its relevance was not immediately recognised. In 1964, the Soviet physicist Yakov Zeldovich and, independently, the American astronomer Edwin Salpeter proposed that the gravitational accretion of matter onto a massive compact object could convert a significant fraction of the accreted mass into energy, far more efficiently than nuclear fusion. The general theory of relativity, formulated by Einstein in 1915, had predicted the existence of objects whose gravitational fields are so strong that nothing, including light, can escape them. The term black hole was not coined until 1967 by John Archibald Wheeler, but the mathematical solutions describing such objects had been known since Carl Schwarzschild's work in 1916 and Roy Kerr's generalization to rotating black holes in 1963. The combination of these theoretical developments pointed toward a picture in which the centers of some galaxies harbor black holes with masses millions or billions of times that of the Sun, and the enormous energy output of quasars is powered by gas falling into these black holes, heating up to extreme temperatures and radiating intensely as it spirals inward through an accretion disk. This model, known as the active galactic nucleus paradigm, was not established overnight. It required the gradual accumulation of evidence from multiple wavelength regimes, radio, infrared, optical, ultraviolet, and eventually X-ray and gamma-ray observations, and the resolution of numerous theoretical puzzles about the structure and physics of accretion disks, relativistic jets, and the interaction between the central engine and the surrounding galaxy. By the 1980s and 1990s, the model had become the standard framework for understanding not only quasars, but a broader family of active galactic nuclei, including Seyfert galaxies, blazars, and radio galaxies, all of which appear to represent the same basic phenomenon viewed from different angles and at different stages of activity. TON 618 sits at the extreme end of this family. When its spectrum was examined in detail, the redshift was determined to be approximately 2.219, which corresponds to a look-back time of roughly 10.4 billion years, meaning the light detected from TON 618 was emitted when the universe was only about 3.4 billion years old, less than a quarter of its current age. The object's apparent magnitude is approximately 15.9, which places it well beyond naked eye visibility, but within reach of moderate telescopes, and when the distance implied by its redshift is taken into account, its absolute luminosity becomes staggering. TON 618 radiates at an estimated luminosity of roughly 4 times 10 to the power of 40 watts, which is approximately 140 trillion times the luminosity of the Sun, making it one of the most luminous objects ever observed in the universe. To put this number into perspective requires stepping through a series of comparisons that progressively reveal just how far outside normal experience it lies. The Sun emits about 3.8 times 10 to the power of 26 watts, and it is an average star, neither particularly luminous nor particularly faint. The most luminous stars known, such as the hypergiant R136A1 in the Large Magellanic Cloud, emit several million times the Sun's luminosity, but even the entire Milky Way galaxy, with its roughly 200 to 400 billion stars, has a total luminosity of only about 5 times 10 to the power of 36 watts, which means TON 618 outshines the entire Milky Way by a factor of nearly 10,000. It is not simply brighter than a galaxy, it is brighter than thousands of galaxies combined, and all of this energy is coming from a region that, while not as small as a single star, is extraordinarily compact compared to a galaxy, concentrated within the innermost region surrounding the central black hole. The mechanism by which this energy is produced is gravitational accretion, and the efficiency of this process is governed by several factors that are worth examining in detail. When matter falls toward a black hole, it does not simply drop straight in. Instead, because of its angular momentum, it settles into a rotating disk of gas known as an accretion disk. Within this disk, friction between adjacent layers of gas moving at slightly different speeds causes the gas to heat up and to slowly spiral inward, losing angular momentum and gaining thermal energy. The temperatures in the innermost regions of the disk can reach millions or even billions of degrees, depending on the mass of the black hole and the rate at which matter is being accreted, and the gas radiates this thermal energy across the electromagnetic spectrum, from radio waves to X-rays. The efficiency of converting accreted mass into radiated energy depends on how close the innermost stable circular orbit of the accretion disk is to the event horizon of the black hole, which in turn depends on whether the black hole is rotating. For a non-rotating, or Schwarzschild black hole, the innermost stable orbit is at 3 times the Schwarzschild radius, and the theoretical efficiency of energy extraction is about 5.7% of the rest mass energy of the accreted material. For a maximally rotating, or Kerr black hole, the innermost stable orbit can be much closer to the event horizon, and the efficiency can be as high as about 42%. Even at the lower end, this efficiency vastly exceeds nuclear fusion, which converts only about 0.7% of rest mass energy into radiation in the most common stellar fusion reactions. This is the fundamental reason why accretion onto black holes can produce such extreme luminosities. Gravity, operating in the regime of strong space-time curvature predicted by general relativity, is a far more efficient energy source than nuclear reactions. The mass of the central black hole in TON 618 was estimated using a technique known as reverberation mapping, supplemented by the analysis of broad emission lines in its spectrum. The basic principle of reverberation mapping relies on the fact that the gas clouds surrounding the central engine of a quasar, known as the broadline region, respond to changes in the luminosity of the accretion disk, with a time delay that corresponds to the light travel time from the disk to the clouds. By measuring this time delay and combining it with the velocity of the clouds, inferred from the Doppler broadening of their emission lines, astronomers can estimate the mass enclosed within the radius of the broadline region. In the case of TON 618, the broad emission lines are exceptionally wide, indicating that the gas clouds are moving at extremely high velocities, which in turn implies an enormous enclosed mass. The most widely cited estimate, published in a 2004 study by Schemmer and colleagues, places the mass of the black hole at approximately 66 billion solar masses, though subsequent analyses using refined calibrations have suggested values that range from about 40 billion to over 100 billion solar masses, depending on the assumptions made about the geometry and dynamics of the broadline region. A mass of 66 billion solar masses is so far beyond the range of most known black holes that it is worth examining the scale more carefully. The black hole at the centre of the Milky Way, Sagittarius A*, has a mass of approximately 4 million solar masses. The black hole at the centre of the giant elliptical galaxy M87, which was the subject of the first Event Horizon Telescope image in 2019, has a mass of approximately 6.5 billion solar masses. TON 618's black hole is roughly 10 times more massive than M87's and roughly 16,500 times more massive than Sagittarius A*. In terms of its Schwarzschild radius, the radius of the event horizon for a non-rotating black hole, which scales linearly with mass, the event horizon of a 66 billion solar mass black hole would extend to approximately 1,300 astronomical units, where 1 astronomical unit is the distance from the Earth to the Sun. This means the event horizon alone would extend well beyond the orbit of Pluto, which lies at roughly 40 astronomical units, and would encompass a sphere with a diameter substantially larger than the entire solar system. If placed at the centre of our solar system, the event horizon would swallow every planet, every dwarf planet, and a significant portion of the Kuiper belt without any of those objects ever approaching a boundary from which they could return. The physical size of the event horizon, however, does not directly correspond to the region from which most of the radiation is emitted. The accretion disk extends far beyond the event horizon, and the most luminous portions are typically concentrated in the inner regions, but can span thousands of Schwarzschild radii. For a black hole of this mass, the accretion disk's luminous region could extend over a volume comparable to or larger than the orbits of the outermost known objects in the solar system, though still tiny compared to the overall scale of the host galaxy. This is one of the reasons quasars can appear point-like. Even though the energetically active region spans what would be a vast distance by human standards, at cosmological distances of billions of light-years, it subtends an angle far too small to be resolved by any current telescope. The question of how a black hole can reach such an enormous mass is one of the most active and challenging areas of research in modern astrophysics, and it connects directly to fundamental questions about the formation and evolution of galaxies, the nature of the early universe, and the physics of accretion. The basic framework is straightforward in principle. A black hole grows by accreting matter, and the more matter it accretes, the more massive it becomes. But in practice, the growth of black holes is constrained by several factors that make it difficult to build up extremely large masses, especially within the limited time available in the early universe. The most important constraint on black hole growth is the Eddington limit, named after the British astrophysicist Arthur Eddington, who first derived it in the context of stellar structure. The Eddington limit describes the maximum luminosity at which an object can radiate while still allowing matter to fall inward against the outward pressure of radiation. When matter is accreted onto a black hole, and the resulting radiation is emitted, The photons interact with the infalling gas and exert an outward force. If the luminosity exceeds the Eddington limit, this outward radiation pressure overcomes the inward gravitational pull, and further accretion is suppressed. The Eddington luminosity scales linearly with the mass of the accreting object, so more massive black holes can accrete at higher rates without exceeding the limit. But even at the Eddington rate, the timescale for doubling the mass of a black hole, known as the Salpeter time, is approximately 45 million years, assuming a canonical efficiency of about 10%. This means that even if a black hole were to accrete continuously at the maximum rate permitted by the Eddington limit, starting from a seed mass of, say, 100 solar masses formed from the collapse of a massive star, it would take many hundreds of millions of years to reach masses of billions of solar masses, and reaching 66 billion solar masses would require even longer. This timescale argument creates a significant tension with observations, because Taunton 618 is seen at a redshift of 2.219, corresponding to a time when the universe was roughly 3.4 billion years old. If the black hole had to grow from a stellar mass seed to 66 billion solar masses within this time, continuous accretion at the Eddington limit would be barely sufficient, and any interruptions in the accretion, any periods of reduced fueling, or any inefficiency in the process would make it impossible. This is the essence of what is sometimes called the black hole mass budget problem, or the seed mass problem, and it has led to several proposed solutions, each of which has its own supporting evidence and unresolved difficulties. One class of solutions involves more massive seeds. Instead of beginning with a stellar mass black hole of roughly 10 to 100 solar masses, formed from the collapse of a massive star at the end of its life, it is possible that some black holes in the early universe formed through more exotic processes that produced much larger initial masses. One such process is the direct collapse of a massive cloud of primordial gas, bypassing the formation of a normal star altogether. In the early universe, before the first generation of stars had enriched the gas with heavy elements, and before the cosmic background radiation had cooled below certain thresholds, large clouds of hydrogen and helium gas could, under specific conditions, collapse directly into black holes with masses of 10,000 to 100,000 solar masses. These so-called direct collapse black holes would have a substantial head start in the mass growth race, requiring far fewer doublings to reach the masses observed in high redshift quasars. The conditions required for direct collapse are quite specific, involving the suppression of molecular hydrogen cooling by a strong background of ultraviolet radiation from nearby star-forming regions, and the details of how frequently these conditions are met in the early universe remain a subject of active investigation through both theoretical modelling and numerical simulation. Another class of solutions involves super-Eddington accretion, periods during which the black hole accretes matter at rates exceeding the nominal Eddington limit. While the Eddington limit is derived under the assumption of spherical symmetry, real accretion flows are not spherically symmetric. They occur through disks and may involve complex geometries in which radiation can escape preferentially in certain directions, while matter continues to fall in from other directions. Numerical simulations of so-called slim accretion disks, in which the accreted gas is optically thick and the photons are partially trapped within the flow and advected inward rather than escaping, suggest that accretion rates of several times the Eddington rate, and possibly much higher, can be sustained for extended periods. If super-Eddington accretion occurred during some phases of the black hole's growth, particularly in the early stages when the seed was small and gas supply was abundant, it could significantly relax the timescale constraints. A third possibility involves the merging of black holes. When galaxies merge, which is a common occurrence throughout cosmic history, the supermassive black holes in their centers can eventually sink to the center of the merged system through dynamical friction and themselves merge, combining their masses. This process does not add energy in the same way as accretion, but it can produce rapid increases in mass through discrete jumps rather than gradual accumulation. The rate at which galaxy mergers contribute to the growth of the most massive black holes is not fully constrained observationally, and theoretical models suggest that while mergers are important, they are probably not sufficient on their own to account for the most extreme masses observed. In the case of TON 618, the precise growth history is unknown and probably unknowable in detail, but the most likely scenario involves some combination of all three factors: a relatively massive seed, possibly formed through direct collapse or through the rapid merger of early stellar mass black holes in a dense nuclear cluster. Extended periods of near-Eddington or super-Eddington accretion fueled by abundant gas supply in the early universe, and one or more major merger events that added additional mass. The fact that TON 618 is seen at a redshift where the universe was already several billion years old provides some additional room for growth compared to the most distant known quasars, which are observed at redshifts above 7, corresponding to times when the universe was less than 800 million years old, but the mass of 66 billion solar masses remains challenging to explain under any single growth mechanism operating within standard assumptions. The luminosity of TON 618, estimated at roughly 4 times 10 to the 40 watts, can be compared to its Eddington luminosity to assess how rapidly it is accreting at the epoch of observation. The Eddington luminosity for a 66 billion solar mass black hole is approximately 8.3 times 10 to the 40 watts, which means TON 618 is radiating at roughly half its Eddington luminosity. This implies that the black hole is still actively accreting at a substantial rate, but is not at the maximum rate permitted by radiation pressure feedback. The corresponding mass accretion rate, assuming a canonical radiative efficiency of about 10%, would be on the order of several hundred solar masses per year, meaning that the black hole is consuming the equivalent of a few hundred suns worth of gas every year and converting roughly 10% of the mass energy of that gas into radiation that escapes the system, producing the observed quasar luminosity. This accretion rate raises immediate questions about the fuel supply. Where does the gas come from, and how is it delivered to the innermost regions around the black hole? In general, the fueling of active galactic nuclei is understood to involve processes operating on a range of spatial scales. On the larger scales, galaxy interactions and mergers can drive gas from the outer regions of galaxies into their centers by torquing the gas through gravitational perturbations. On intermediate scales, bars and spiral arms in disk galaxies can channel gas inward, and on the smallest scales, turbulence, magnetic fields, and radiative processes in the gas determine how efficiently it loses angular momentum and falls into the accretion disk. For the most luminous quasars, which require enormous fuel supply sustained over millions of years, major galaxy mergers are often invoked as the primary triggering mechanism because they can concentrate large quantities of gas in the nuclear region and sustain high accretion rates for extended periods. TON 618's host galaxy has been difficult to study directly, precisely because the quasar itself is so luminous that it overwhelms the light of the surrounding galaxy. This is a common problem with bright quasars. The point-like nucleus can be hundreds or thousands of times brighter than the extended galaxy in which it resides, making it extremely challenging to detect and characterize the host galaxy's properties. Some observations, particularly those using adaptive optics on large ground-based telescopes, and those conducted in the infrared, where the contrast between the quasar nucleus and the host galaxy is somewhat reduced, have provided tentative evidence that TON 618 resides in a massive galaxy, possibly a giant elliptical, consistent with the expectation that the most massive black holes are found in the most massive galaxies. But the details of the host galaxy's morphology, stellar mass, star formation rate, and merger history remain poorly constrained. The relationship between the mass of a central black hole and the properties of its host galaxy is itself one of the most important discoveries in extragalactic astronomy over the past 3 decades. In the late 1990s and early 2000s, several groups of researchers, notably John Cormandy and Douglas Richstone, Laura Ferraris and David Merritt, and Carl Gebhardt and colleagues, demonstrated that the masses of supermassive black holes in nearby galaxies are correlated with the velocity dispersion of stars in the galaxy's bulge, the central, roughly spherical component of the galaxy, and with the total mass and luminosity of the bulge. These correlations, known collectively as the M-sigma relation and related scaling relations, are tight enough to suggest that the growth of the black hole and the growth of the galaxy's bulge are somehow coupled, even though the black hole's sphere of gravitational influence, the region within which the black hole's gravity dominates over the gravity of the surrounding stars, is tiny compared to the overall size of the bulge. The physical mechanism responsible for this coupling is generally believed to involve feedback, energy and momentum released by the accreting black hole in the form of radiation. Winds and jets interact with the surrounding gas, heating it, expelling it, or preventing it from cooling and forming stars. This feedback can regulate both the growth of the black hole itself by limiting its fuel supply and the star formation in the host galaxy, by reducing the availability of cold, dense gas from which stars can form. The details of how feedback operates, the relative importance of different feedback modes, and the extent to which feedback is responsible for the observed scaling relations are all subjects of intensive ongoing research, with large-scale cosmological simulations playing an increasingly important role alongside observational studies. TON 618 presents an interesting test case for these scaling relations. If the M-sigma relation and related correlations are used to predict the expected black hole mass for a galaxy that hosts a 66 billion solar mass black hole, the implied galaxy would need to be extraordinarily massive, with a velocity dispersion exceeding 400 or even 500 kilometers per second and a stellar mass of many trillions of solar masses. Such galaxies exist in the local universe. They are the brightest cluster galaxies, the giant elliptical galaxies that sit at the centers of the most massive galaxy clusters. And some estimates suggest that TON 618's host galaxy is indeed in this mass range. However, the uncertainties in the black hole mass, the host galaxy properties, and the intrinsic scatter in the scaling relations are all large enough that definitive conclusions cannot yet be drawn. It remains possible that TON 618's black hole is somewhat overmassive relative to its host galaxy, or that the scaling relations at the very highest masses differ from those observed at more typical masses. The question of whether there is an upper limit to the mass that a black hole can attain is closely related to the physics of accretion, feedback, and the availability of gas in the most massive galaxies. Some theoretical arguments suggest that the most massive black holes should have masses in the range of tens of billions of solar masses, set by the point at which feedback from the accreting black hole is powerful enough to expel or heat all of the available gas in even the most massive galaxies, effectively shutting down further growth. Other arguments, based on the maximum density of gas that can be concentrated in galactic nuclei and the finite time available for accretion in the age of the universe, arrive at similar upper limits. TON 618, with its estimated mass of 66 billion solar masses, is close to, or possibly at these theoretical limits, making it a valuable object for testing models of black hole growth and the coevolution of black holes and galaxies. There are a few other objects with comparably extreme estimated masses. The black hole in the galaxy, Holm 15A, a brightest cluster galaxy in the Abell 85 cluster, has been estimated at approximately 40 billion solar masses based on stellar dynamical modeling. Phoenix A, the central galaxy of the Phoenix cluster, harbors a black hole estimated at roughly 100 billion solar masses in some analyses. Though these estimates carry substantial uncertainties, the challenge with all of these extreme mass estimates is that the observational techniques used to measure black hole masses each have their own systematic uncertainties and assumptions, and at the very highest masses, the samples are so small that statistical corrections and calibrations are unreliable. Reverberation mapping, which was used for TON 618, requires assumptions about the geometry of the broadline region and the relationship between the measured time lag and the true radius of the emitting gas. Stellar dynamical modeling, used for nearby galaxies like Holm 15A, requires high spatial resolution to resolve the black hole's sphere of influence and assumes a particular distribution of stellar orbits. Gas dynamical modeling, used in some cases, assumes that the gas is in ordered rotation and is not significantly affected by non-gravitational forces. Each of these methods has been extensively calibrated and tested, but systematic uncertainties at the level of a factor of 2 or more are not uncommon, particularly at the extremes of the mass distribution. The spectrum of TON 618, beyond revealing the redshift and the broad emission lines used for mass estimation, contains a wealth of information about the physical conditions in the immediate environment of the black hole. The ultraviolet and optical continuum emission, which arises primarily from the accretion disk, shows the characteristic shape expected from a multi-temperature blackbody disk, modified by the effects of electron scattering, and possibly by the presence of a hot corona above the disk that can Compton scatter photons to higher energies, producing the X-ray emission that is observed from many quasars. The broad emission lines, particularly the hydrogen Balmer lines and the lines of ionized carbon, magnesium and iron, are produced by gas clouds in the broadline region, which is located at distances of roughly light weeks to light months from the central black hole, moving at velocities of thousands of kilometers per second. The widths of these lines, measured as the full width at half maximum or the velocity dispersion, are among the key inputs to the mass estimation, and in TON 618, the line widths are exceptionally large, consistent with the enormous enclosed mass. The broad emission lines also carry information about the chemical composition of the gas, which in turn provides clues about the history of star formation in the host galaxy. The gas in the broad line region has been enriched by nuclear processing in stars, and the relative strengths of emission lines from different elements can be used to estimate the metallicity of the gas, that is, the abundance of elements heavier than hydrogen and helium. In general, high-luminosity quasars at high redshifts tend to show solar or supersolar metallicities in their broadline regions, indicating that substantial star formation and chemical enrichment had already occurred in their host galaxies before the epoch at which they are observed. For TON 618, the metallicity indicators are consistent with this trend, suggesting that the galaxy hosting the quasar had already undergone significant star formation by the time the universe was roughly 3.4 billion years old. Moving outward from the broadline region, quasar spectra often show narrow emission lines produced by gas at greater distances from the nucleus in the narrow line region, where the velocities are lower and the densities are much lower than in the broadline region. The narrow line region can extend over kiloparsec scales, comparable to the size of the host galaxy, and its properties are influenced both by the ionizing radiation from the quasar and by the interstellar medium of the galaxy. In some quasars, the narrow emission lines show blue-shifted components indicating outflowing gas, which is interpreted as evidence for quasar-driven winds or outflows that may be carrying mass and energy into the interstellar and circumgalactic medium, potentially contributing to the feedback processes that regulate galaxy growth. TON 618 has also been studied in the X-ray regime, where observations with satellites such as Chandra and XMM Newton have detected emission consistent with the expected properties of a luminous quasar. The X-ray emission from quasars is thought to arise primarily from the Comptonization of ultraviolet photons from the accretion disk by hot electrons in a corona or a magnetically heated region above the disk. The X-ray spectrum, including its shape, luminosity and variability, provides constraints on the temperature and optical depth of the corona and on the geometry of the innermost accretion flow. For the most luminous quasars, the ratio of X-ray to optical luminosity tends to be lower than for less luminous, active galaxies, a trend known as the alpha-ox relation, and TON 618 follows this trend, emitting relatively less X-ray radiation per unit of optical luminosity than a typical Seyfert galaxy, consistent with the hypothesis that the X-ray corona becomes less efficient or is somehow geometrically modified in the most powerful quasars. The radio properties of TON 618 are also noteworthy, though perhaps less extreme than its optical and ultraviolet luminosity would suggest. TON 618 was originally identified as a radio source, but it is classified as a radio-quiet quasar, meaning that its radio emission is relatively weak compared to its optical emission. The distinction between radio-loud and radio-quiet quasars, which was one of the early observational puzzles in quasar research, is now understood to be related to the presence or absence of powerful, relativistic jets, collimated outflows of plasma moving at speeds close to the speed of light, launched from the immediate vicinity of the black hole. Radio-loud quasars, which account for roughly 10 to 15% of the total quasar population, have prominent jets that emit synchrotron radiation at radio wavelengths, while radio-quiet quasars have much weaker or absent jets. The physical factor that determines whether a quasar is radio-loud or radio-quiet is not fully understood, but the leading hypothesis is that the spin of the black hole plays a critical role. Rapidly spinning black holes can more efficiently extract rotational energy to power jets through mechanisms related to the Blandford-Znajek process, in which magnetic fields threading the ergosphere of a rotating black hole extract energy from the black hole's rotation. The fact that TON 618 is radio-quiet might therefore indicate that its black hole is not maximally spinning, or it might reflect other factors related to the magnetic field configuration or the properties of the accreting gas. The variability of quasars, including TON 618, is another source of information about the physics of the central engine. Quasars are known to vary in brightness on timescales ranging from hours to years, with the amplitude and timescale of variability providing constraints on the size and structure of the emitting region. The basic argument is that a region cannot vary coherently on a timescale shorter than the light crossing time of that region, so rapid variability implies a compact emitting region. For the most luminous quasars, including TON 618, the variability tends to be relatively modest in amplitude, on the order of a few tenths of a magnitude over timescales of months to years, consistent with the expectation that the emitting region is large, as would be the case for an accretion disk around an extremely massive black hole, where the innermost stable orbit and the associated emitting region span many hundreds of astronomical units. However, the interpretation of quasar variability is complicated by the fact that the observed variability includes contributions from the accretion disk, the X-ray corona, and possibly from the reprocessing of radiation by surrounding material, each of which can vary on different timescales and for different physical reasons. Additionally, for distant quasars like TON 618, the observed variability timescale is affected by cosmological time dilation. The time between emission and observation is stretched by a factor of 1 plus z, so observed timescales are longer than the intrinsic timescales by a factor of approximately 3.2 for TON 618. This effect must be accounted for when comparing the variability properties of quasars at different redshifts. The environment of TON 618 on larger scales is also of interest, though it is more difficult to study. Luminous quasars at redshifts around 2 are expected to reside in regions of the universe that are overdense in galaxies and matter. Since the most massive galaxies and black holes tend to form in the densest environments, the peaks of the initial density fluctuations that seeded the formation of large-scale structure. Observational surveys have attempted to characterize the environments of high redshift quasars by mapping the distribution of galaxies around them, looking for statistical excesses of galaxies above the background level. The results are mixed. Some studies find evidence for overdensities around luminous quasars, while others do not, possibly reflecting the diversity of environments and the difficulty of detecting faint galaxies at high redshifts. For TON 618 specifically, detailed environmental studies are limited, but the expectation, based on its extreme black hole mass and luminosity, is that it resides in a region that will eventually evolve into a massive galaxy cluster, with the quasar's host galaxy becoming the brightest cluster galaxy. The evolution of quasars over cosmic time is itself a rich subject that provides context for understanding TON 618. The cosmic quasar luminosity function, which describes the number density of quasars as a function of luminosity and redshift, shows a dramatic peak at redshifts around 2 to 3, an epoch sometimes referred to as cosmic noon, because it also coincides with the peak of the global star formation rate density. At this epoch, the conditions for fueling supermassive black holes, including the availability of cold gas, the frequency of galaxy interactions and mergers, and the general density of the universe were apparently optimal, and the most powerful quasars, including TON 618, lit up the universe with luminosities that have not been matched at lower redshifts. Since redshift 2, the quasar population has declined dramatically. The most luminous quasars have essentially disappeared from the local universe, and the typical luminosities of active galactic nuclei have decreased by orders of magnitude. The supermassive black holes themselves have not disappeared. They remain at the centers of galaxies, but they are now largely dormant or accreting at very low rates, no longer producing the spectacular energy output that characterizes the quasar phase. The black hole at the center of the Milky Way, Sagittarius A star, is a case in point. Despite its mass of 4 million solar masses, it is currently accreting at an extraordinarily low rate and radiating at only about 10 to the minus 8 times its Eddington luminosity, making it one of the faintest known active galactic nuclei in absolute terms. This decline in quasar activity is closely connected to the broader evolution of galaxies. As the universe expands, the gas supply that fuels both star formation and black hole accretion diminishes. The cosmic density of neutral hydrogen, the raw material for star formation and accretion, has decreased since redshift 2, and the processes that convert gas into stars and feed it into black holes have become less efficient as galaxies have grown more massive, as their halos have become hotter, and as feedback from previous episodes of star formation and AGN activity has heated or expelled gas from the galactic environment. The result is a universe in which the most massive black holes, like the one in TON 618, are relics of a more active past, sitting quietly at the centres of massive galaxies and growing little if at all in the present epoch. The idea of black holes as relics raises an interesting conceptual point about the nature of information in astrophysics. Everything known about TON 618's black hole is inferred indirectly, no direct image of the event horizon exists, no probe has been sent to measure its mass, and no observation can penetrate the event horizon to reveal what lies within. The mass is estimated from the dynamics of surrounding gas. The luminosity is inferred from the observed flux and the distance. The spin is effectively unconstrained, and the internal state of the black hole is, according to general relativity, completely hidden from external observers. The no-hair theorem, a result in classical general relativity, states that a black hole in equilibrium is fully characterized by only three externally measurable quantities: its mass, its angular momentum, spin, and its electric charge, the last of which is negligible for astrophysical black holes. All other information about the matter that fell into the black hole, its composition, its structure, its history, is lost to external observers, at least in the classical theory. Whether information is truly lost or is somehow preserved in subtle correlations in the Hawking radiation that a black hole emits as it slowly evaporates is one of the deepest open questions in theoretical physics, touching on the interface between general relativity and quantum mechanics. For a black hole as massive as TON 618's, Hawking radiation is utterly negligible. The temperature of the Hawking radiation is inversely proportional to the mass of the black hole, and for a 66 billion solar mass black hole, the temperature is approximately 10 to the minus 18 Kelvin, far below the current temperature of the cosmic microwave background, meaning the black hole is effectively absorbing energy from its surroundings far faster than it could ever radiate it away. The evaporation timescale for such a black hole, even if it were placed in a completely empty universe, with no matter or radiation to absorb, would be on the order of 10 to the 100 years or more, a timescale so far beyond the current age of the universe, roughly 13.8 billion years, that it is essentially infinite for all practical purposes. The discovery and characterization of TON 618 did not occur as a single dramatic event, but unfolded gradually over decades, through the accumulation of observations across multiple wavelength regimes by multiple research groups using progressively more capable instruments. The original identification as a radio source in the Tonnentzindler catalogue was followed by optical spectroscopy that revealed its high redshift and quasar nature. Subsequent observations measured its optical and ultraviolet luminosity, its broad emission line properties, its X-ray emission, and its radio characteristics. The mass estimate of the central black hole emerged from the application of virial mass estimation techniques to the broad emission lines, calibrated against samples of lower luminosity AGN for which masses had been estimated through more direct methods such as reverberation mapping and stellar dynamical modelling. Each step in this process involved its own set of assumptions, calibrations and uncertainties, and the resulting portrait of TON 618 is a composite constructed from many independent lines of evidence, each of which contributes to the overall picture, while also introducing its own sources of error. This point about the composite, constructed nature of astrophysical knowledge is worth emphasizing because it contrasts with the way extreme objects like TON 618 are sometimes presented in popular accounts, where the emphasis tends to be on the spectacle of the numbers, the enormous mass, the staggering luminosity, the incomprehensible size of the event horizon, at the expense of the careful, incremental, often ambiguous process by which these numbers are determined. The mass of 66 billion solar masses is not a direct measurement in the way that one might weigh an object on a scale. It is an inference drawn from observed spectral properties, filtered through a theoretical model of the dynamics of gas around a central gravitating body, calibrated against other systems where independent mass measurements are available, and subject to systematic uncertainties that could easily shift the estimate by a factor of 2 in either direction. This does not mean the estimate is unreliable. The methods used are well tested, extensively calibrated, and consistent with independent lines of evidence. But it does mean that the number should be understood as a best current estimate within a framework, not as a precisely known quantity. Similarly, the luminosity of TON 618 is an estimate that depends on the assumed distance, which is derived from the redshift under the assumption that the redshift is entirely due to the expansion of the universe, the assumed cosmological model which determines the relationship between redshift and luminosity distance, and the assumed spectral energy distribution, which determines how much of the total luminosity is emitted at wavelengths that are actually observed versus wavelengths that are inferred by extrapolation. The standard cosmological model, known as the lambda-CDM model, which includes cold dark matter and a cosmological constant representing dark energy, is well supported by multiple independent lines of evidence and provides a reliable framework for these calculations, but it is itself subject to ongoing refinement and potential revision, particularly regarding the precise values of key parameters such as the Hubble constant, which determines the overall scale of distances in the universe, and has been the subject of a notable tension between different measurement methods in recent years. The history of the scientific understanding of objects like TON 618 is also a history of the development and deployment of observational technology. The discovery of quasars was made possible by the advent of radio astronomy in the decades following World War II, which itself was an outgrowth of wartime radar technology. The identification of quasars with distant luminous objects required the combination of radio observations with optical spectroscopy, using large ground-based telescopes, and the measurement of their physical properties has progressively incorporated data from virtually every part of the electromagnetic spectrum, from radio to gamma rays, using both ground-based and space-based facilities. The Hubble Space Telescope, launched in 1990, provided the angular resolution needed to detect host galaxies around bright quasars for the first time. X-ray satellites such as ROSAT, Chandra, and XMM Newton revealed the high-energy emission from quasar coronae and jets. Infrared observatories, including Spitzer, and more recently the James Webb Space Telescope, have opened windows into the thermal emission from dust heated by the quasar, and have enabled the study of host galaxies at high redshifts, where optical light is shifted into the infrared. Millimeter and submillimeter arrays, particularly the Atacama Large Millimeter Array, have provided unprecedented resolution and sensitivity for studying the molecular gas content of quasar-host galaxies, directly tracing the fuel supply for both star formation and black hole accretion. The James Webb Space Telescope, which began scientific operations in 2022, is expected to contribute significantly to the study of the most luminous quasars and their host galaxies, including objects like TON 618, by providing deep infrared imaging and spectroscopy that can separate the point-light quasar emission from the extended emission of the host galaxy, measure the stellar populations and star formation histories of host galaxies, and detect companion galaxies and large-scale structures in the quasar environment. Early results from JWST have already revealed surprises about the relationship between black holes and their host galaxies at high redshifts, with some observations suggesting that black holes in the early universe may be overmassive, relative to their host galaxies compared to the local scaling relations, which could have implications for models of coevolution and feedback. The broader context for understanding TON 618 and other extreme quasars includes the cosmological framework of structure formation, which describes how the initial, nearly uniform distribution of matter in the early universe, imprinted by quantum fluctuations during inflation, evolved through gravitational instability into the complex hierarchy of structures, galaxies, groups, clusters, filaments, and voids observed in the universe today. In this framework, the first black holes formed from the first generation of stars, known as population 3 stars, which are thought to have been much more massive than typical present-day stars due to the absence of heavy elements and the associated cooling mechanisms. These stars would have had masses of tens to hundreds of solar masses, and some of them may have collapsed directly into black holes at the end of their lives, providing the initial seeds around which supermassive black holes could grow. Alternatively, as mentioned earlier, direct collapse of large gas clouds could have produced more massive seeds, and the relative importance of these different seeding mechanisms remains an open question. Once formed, the seed black holes would have grown through accretion and mergers within the hierarchical merging of dark matter halos and galaxies. The most massive black holes would have tended to form in the most massive halos, where the gas supply was most abundant and where galaxy mergers were most frequent. The detailed growth history of any individual black hole depends on the specific merger history of its host halo, the accretion rate at each epoch, the efficiency of feedback in regulating accretion, and many other factors that vary from one system to another. Large cosmological simulations such as Illustri's Eagle and their successors attempt to model these processes self-consistently, tracking the formation and evolution of millions of galaxies and their central black holes over billions of years within a cosmologically representative volume. These simulations have achieved considerable success in reproducing many observed properties of the galaxy and black hole populations, including the scaling relations between black hole mass and galaxy properties, the quasar luminosity function, and the global trends in star formation and accretion activity over cosmic time. However, the most extreme objects, those at the tails of the mass and luminosity distributions, remain challenging for simulations, both because they are rare and require very large simulation volumes to capture statistically, and because the physical processes governing their growth may involve physics that is not fully captured by current subgrid models. The concept of the event horizon itself, which defines the boundary of a black hole, is one of the most profound predictions of general relativity, and one that has only recently been subject to direct observational test. The Event Horizon Telescope collaboration's images of the shadows of the black holes in M87 and the Milky Way, released in 2019 and 2022 respectively, provided the first visual evidence consistent with the existence of event horizons, showing a bright ring of emission surrounding a dark central region, the shadow, whose size and shape are consistent with the predictions of general relativity for a black hole of the estimated mass. For TON 618, the angular size of the event horizon shadow, as seen from Earth, would be far too small to resolve with any current or planned instrument. Despite the enormous physical size of the event horizon, the distance to TON 618 is so vast that the angular size is many orders of magnitude smaller than the resolution achieved by the Event Horizon Telescope. Direct imaging of TON 618's event horizon is therefore not feasible with current technology, and all information about the black hole must continue to be inferred indirectly from the properties of the radiation emitted by the surrounding accretion flow. The thermodynamics of black holes, a subject that connects general relativity, quantum field theory, and statistical mechanics, provides a deeper theoretical context for understanding objects, like the black hole in TON 618. In the early 1970s, Jacob Bekenstein and Stephen Hawking established that black holes have entropy proportional to the area of their event horizon and a temperature inversely proportional to their mass. These results, known as the laws of black hole thermodynamics, are formally analogous to the laws of ordinary thermodynamics and have profound implications for our understanding of the fundamental nature of space, time, and information. The entropy of the black hole in TON 618, calculated from its event horizon area, is extraordinarily large, on the order of 10 to the 99 or more in natural units, making it one of the highest entropy objects in the observable universe. This enormous entropy reflects the vast number of microstates, quantum configurations of the black hole's interior, that are consistent with the externally observed macroscopic properties of mass, spin, and charge. The nature of these microstates and how they are encoded in the structure of space-time is one of the central open questions in theoretical physics, with approaches ranging from string theory to loop quantum gravity to the holographic principle attempting to provide a microscopic accounting of black hole entropy. Returning to the astrophysical perspective, TON 618 also serves as a useful reference point for discussing the cosmic census of supermassive black holes. Every massive galaxy in the local universe is believed to harbour a supermassive black hole at its centre, based on decades of dynamical studies and the success of the active galactic nucleus paradigm in explaining observed nuclear activity. The total mass density of supermassive black holes in the local universe, integrated over all galaxies, has been estimated to be on the order of 4 times 10 to the 5th solar masses per cubic megaparsec, and this mass density is consistent with what would be expected if the black holes grew primarily through radiatively efficient accretion during the quasar era, as inferred from the integrated light of all quasars over cosmic history, an argument first articulated by Andrei Solton in 1982, and known as the Solton argument. The Solton argument provides an elegant consistency check. The total energy radiated by all quasars over the history of the universe, when converted back into accreted mass using an assumed radiative efficiency, yields a total black hole mass density that agrees well with the locally observed value, supporting the picture in which most of the mass of supermassive black holes was accreted during luminous quasar phases. The implications of this argument for the most massive individual black holes are that they are expected to have passed through one or more luminous quasar phases during their growth, and the duration and luminosity of these phases depend on the total mass accreted and the rate of accretion. For a black hole as massive as the one in TON 618, the cumulative energy radiated over its entire growth history, assuming an average radiative efficiency of 10%, would be approximately 1.2 times 10 to the 55 joules, equivalent to the total energy output of the Sun over about 10 to the 21 years, or roughly 100 billion times the current age of the universe. This is an almost unimaginable quantity of energy, radiated into the intergalactic medium over a period that, while long by human standards, may have been relatively brief, perhaps a few 100 million years, in the context of cosmic history. The impact of this radiated energy on the surrounding environment is another important consideration. Quasar radiation, particularly in the ultraviolet and X-ray bands, can ionize and heat gas over enormous volumes, potentially influencing the thermal state of the intergalactic medium, the rate of star formation in neighboring galaxies, and the chemical enrichment of circumgalactic gas through radiation-driven winds. The concept of quasar proximity zones, regions around high redshift quasars, where the intergalactic medium has been ionized by the quasar's radiation, has been used to study the ionization state of the universe during and after the epoch of reionization, the period when the first sources of ultraviolet light ionized the hydrogen gas that permeated the universe after the cosmic microwave background decoupled. While TON 618 is at a redshift below the epoch of reionization, which is generally placed at redshifts above 6, its immense luminosity would have created a large ionized region around it, influencing the properties of the intergalactic gas in its vicinity. The study of TON 618 and other extreme quasars also connects to broader questions about the role of black holes in shaping the large-scale properties of the universe. The energy output of active galactic nuclei, integrated over all quasars and active galaxies across cosmic history, is a significant fraction of the total energy output of the universe from all sources, and this energy is not emitted uniformly but is concentrated in the most massive halos, where the most powerful quasars reside. The resulting feedback, in the form of heating and outflows, is now recognized as an essential ingredient in models of galaxy formation, without which simulations produce galaxies that are too massive, too blue, and too rich in cold gas compared to observations. The specific role of AGN feedback in quenching star formation in massive galaxies, maintaining the hot atmospheres of galaxy clusters, and regulating the growth of the most massive black holes is a subject of intense current research, with observations of individual systems complementing statistical analyses and cosmological simulations. In the context of the future evolution of the universe, the black hole in TON 618, like all supermassive black holes, will persist for an extraordinarily long time. Long after the stars in its host galaxy have exhausted their nuclear fuel, long after the last white dwarfs and neutron stars have cooled to the background temperature of the universe, long after the galaxies in its group or cluster have merged into a single, large, elliptical galaxy, the black hole will remain, slowly growing through the occasional accretion of stray matter and gradually losing mass through the infinitesimally slow process of Hawking radiation. The timescale for a 66 billion solar mass black hole to evaporate through Hawking radiation is on the order of 10 to the 100 years or beyond, a number so vastly larger than the current age of the universe that it defies any meaningful comparison with processes on human or even cosmic timescales. In this sense, the most massive black holes in the universe are among the most enduring structures that will ever exist, outlasting stars, planets, galaxies, and perhaps even the protons and neutrons from which ordinary matter is composed, if proton decay occurs as some grand unified theories predict. The comparative study of the most massive known black holes, including TON 618, M87's black hole, the black holes in NGC 1600, NGC 4889, IC 1101, Holm 15A and Phoenix A, reveals both commonalities and differences that constrain models of black hole growth. These objects span a range of estimated masses from roughly 10 billion to perhaps 100 billion solar masses, and they are found in a variety of galaxy types and environments, from isolated massive ellipticals to brightest cluster galaxies. The environments of these galaxies vary from relatively isolated groups to the densest known galaxy clusters, and the merger histories and accretion histories of the central black holes are correspondingly diverse. What they share is the requirement that enormous quantities of matter, on the order of tens of billions of solar masses, must have been assembled in the nuclear regions of these galaxies and accreted onto the black holes over the course of billions of years through a combination of gas accretion and black hole mergers, with the details varying from system to system. The gravitational wave signature of black hole mergers involving supermassive black holes is of particular interest in the context of current and planned gravitational wave observatories. The Laser Interferometer Space Antenna, LISA, an ESA-led space mission currently planned for launch in the 2030s, is designed to detect gravitational waves in the millihertz frequency range, which corresponds to the orbital frequencies of binary supermassive black holes in the final stages of their inspiral and merger. If two black holes of tens of billions of solar masses were to merge, the resulting gravitational wave signal would be at extremely low frequencies, at the low end or possibly below the LISA sensitivity band, depending on the precise masses and orbital parameters. Pulsar timing arrays, which use the precisely timed radio pulses from millisecond pulsars to detect gravitational waves with periods of years to decades, are sensitive to even lower frequencies and have recently reported evidence for a stochastic gravitational wave background that is consistent with the expected signal from the cosmic population of inspiraling supermassive black hole binaries. The most massive individual binaries, if they exist, would contribute to this background and might eventually be resolved as individual sources with improved sensitivity. The detection of gravitational waves from mergers of the most massive black holes would provide a completely independent measurement of their masses, complementing and cross-checking the electromagnetic mass estimates, and would also provide information about the spin and orbital parameters of the merging system that cannot be obtained from electromagnetic observations alone. This prospect illustrates how the study of extreme objects like TON 618 is not a closed chapter, but an ongoing endeavour that will continue to be shaped by new observational capabilities and theoretical developments. An additional aspect of the significance of TON 618 concerns its role as a benchmark in the calibration and testing of quasar models. Because it is among the most luminous and best studied quasars at its redshift, TON 618 is frequently used as a reference point in studies of the quasar luminosity function, the black hole mass function, and the relationship between accretion rate and luminosity. Its properties set empirical constraints on the maximum luminosities and masses that models must be able to reproduce, and any model that fails to account for the existence of objects like TON 618, or that predicts such objects should be far more or far less common than they are observed to be, must be revised or reconsidered. In this sense, TON 618 is not merely a curiosity or a record holder, but a scientifically important data point that contributes to the collective understanding of black hole growth and galaxy evolution. The physical processes occurring in the immediate vicinity of TON 618's black hole, within the accretion disk and the surrounding magnetized plasma, involve some of the most extreme conditions found anywhere in the universe. The gas in the inner accretion disk reaches temperatures of millions of degrees, and the densities, while high by interstellar standards, are low enough that the gas is optically thin to many wavelengths of radiation, allowing photons to escape and carry energy and information to distant observers. The magnetic fields in the disk, which are amplified by the differential rotation of the gas through the magnetorotational instability, play a crucial role in transporting angular momentum outward through the disk, enabling matter to spiral inward and accrete onto the black hole. The resulting magnetohydrodynamic turbulence is a complex multi-scale phenomenon that is studied primarily through numerical simulations, as the equations governing it are nonlinear and do not admit simple analytical solutions. State-of-the-art simulations using general relativistic magnetohydrodynamics, known as GRMHD, can now model the structure of accretion flows around spinning black holes with considerable detail, producing synthetic observations that can be compared directly with data from the Event Horizon Telescope and other instruments. The jets that are launched from some accreting black holes, though absent or weak in the case of TON 618, are another manifestation of the extreme physics of the inner accretion flow. In radio-loud quasars and radio galaxies, jets of relativistic plasma extend from the immediate vicinity of the black hole outward to distances of hundreds of kiloparsecs or even megaparsecs, depositing enormous quantities of energy into the intergalactic medium and inflating vast lobes of radio-emitting plasma. The mechanism by which jets are launched and collimated is believed to involve the coupling of the black hole's spin to the magnetic field of the accretion disk, as described by the Blandford-Znajek process, and the resulting jet power can be comparable to or even exceed the radiative luminosity of the accretion disk. The absence of powerful jets in TON 618, despite its enormous black hole mass and high accretion rate, may be related to the spin state of the black hole, the configuration of the magnetic field, or other factors that are not yet fully understood, and it illustrates the diversity of behaviors exhibited by accreting supermassive black holes. In the broader landscape of extreme astrophysical objects, TON 618 occupies a distinctive niche. It is not the most distant quasar known. That distinction is currently held by objects at redshifts above 7, seen when the universe was less than 700 million years old. Nor is it necessarily the most massive black hole, given the uncertainties in mass estimates and the existence of several other candidates with comparably extreme masses. But the combination of its extreme mass, its high luminosity, its location at a redshift that places it near the peak of cosmic quasar activity, and the quality and extent of the observational data available for it make it one of the most important and frequently studied objects of its kind. Its name, derived from a catalogue entry that was originally just a number in a list of radio sources, has become a shorthand in popular and scientific discussions for the upper extremes of black hole mass, and it serves as a reminder that the universe contains objects whose properties lie far outside the range of everyday experience or intuitive comprehension. The study of TON 618 and other ultramassive black holes is also deeply connected to questions about the nature of gravity itself. General relativity, which provides the theoretical foundation for understanding black holes, has been tested with extraordinary precision in the weak field regime. The regime relevant to the solar system, the orbits of binary pulsars, and even the mergers of stellar mass black holes detected by LIGO and Virgo. But the strong field regime, the regime of space-time curvature immediately outside and at the event horizon of a supermassive black hole, is less directly tested, and some modifications to general relativity predict observable differences in the behavior of matter and radiation near the event horizon. The Event Horizon Telescope, images of M87 and Sagittarius. A star have been used to constrain some of these alternative theories, and future observations with improved sensitivity and resolution will continue to push these tests to greater precision. For the most massive black holes like TON 618, the spacetime geometry near the event horizon is, in one sense, less extreme than for smaller black holes. The tidal forces at the event horizon, which are inversely proportional to the square of the mass, are weaker for more massive black holes, meaning that an observer falling through the event horizon of a 66 billion solar mass black hole would experience remarkably gentle tidal forces, far too weak to be physically disruptive, in stark contrast to the intense tidal disruption that would occur near the event horizon of a stellar mass black hole. This counterintuitive result, a direct consequence of the scaling of spacetime curvature with mass, means that the event horizon of an ultramassive black hole is, locally, an unremarkable region of space, and an observer crossing it would notice nothing unusual, even as they pass the point of no return beyond which escape becomes impossible. This property of the event horizon connects to deeper questions about the nature of black hole interiors and the fate of matter that falls in. According to classical general relativity, matter falling into a non-rotating black hole inevitably reaches a singularity at the center, a point of infinite density and curvature where the known laws of physics break down. For a rotating black hole described by the Kerr metric, the situation is more complex. The singularity takes the form of a ring rather than a point, and the mathematical solution admits the possibility of passing through the ring singularity into other regions of space-time, though the physical relevance of these features is debated, as they may be artifacts of the idealized perfectly symmetric solution. The expectation among most physicists is that quantum gravitational effects, which become important at the Planck scale, will modify the classical singularity, but a complete theory of quantum gravity does not yet exist, and the nature of the black hole interior remains one of the deepest open questions in fundamental physics. For an observer studying TON 618 from the outside, these questions are in a sense academic, since no information can escape the event horizon and no external observation can probe the interior. but they are scientifically important because they touch on the fundamental consistency of our physical theories and the ultimate nature of space-time. The legacy of TON 618 in the scientific literature and in public discourse reflects the broader trajectory of our engagement with the extreme universe. When it was first catalogued in the late 1950s, it was a nondescript radio source with a numerical designation, one of thousands of entries in a survey catalogue that most astronomers would never have occasion to examine in detail. Its identification as a quasar placed it in a category of objects that was itself only just being recognised and understood. The estimation of its black hole mass, published decades later, elevated it to a position of special significance as one of the most massive known black holes, and subsequent studies have refined and contextualised this estimate within the broader framework of black hole demographics and galaxy evolution. At each stage, the understanding of TON 618 has been shaped by the available technology, the prevailing theoretical framework, and the accumulated body of observational evidence, and at each stage, the object has served as both a confirmation and a challenge to existing models. The process by which astrophysical knowledge advances is well illustrated by the case of TON 618. It involves not a single decisive observation, but a long sequence of incremental measurements, theoretical developments, and calibrations, each building on what came before and each subject to revision in light of new evidence. The mass of 66 billion solar masses is not a fixed final answer, but a current best estimate within a particular framework, and it may be revised upward or downward as new data become available, as calibration techniques improve, and as our understanding of the systematics of mass estimation deepens. This is not a weakness of the scientific process, but a strength. It reflects the commitment to evidence-based reasoning and the willingness to update conclusions in light of new information that is the hallmark of a mature scientific discipline. The position of TON 618 within the cosmic web, the large-scale filamentary structure of the universe composed of dark matter, gas, and galaxies, is another layer of context that connects it to the broader story of cosmic evolution. The cosmic web formed through the gravitational amplification of primordial density fluctuations, and its nodes, where filaments intersect, are the sites where the most massive galaxy clusters form. The most massive black holes are expected to reside in or near these nodes, where the density of matter is highest and the merger rate of galaxies is greatest. The detailed mapping of the cosmic web at redshift 2 is still in its early stages, as it requires deep, wide-field surveys capable of identifying large numbers of galaxies and tracing their spatial distribution, but current data are consistent with the general picture in which luminous quasars like TON 618 trace the overdense regions that will evolve into massive clusters by the present day. The energetics of the cosmic web itself are influenced by the feedback from active galactic nuclei, including quasars like TON 618. The energy injected by quasar winds and jets into the intergalactic medium can heat the gas in filaments and halos, affecting the rate at which gas cools, falls into galaxies, and forms stars. This feedback is not uniformly distributed but is concentrated around the most active nuclei, creating a complex interplay between the growth of black holes, the evolution of galaxies, and the thermodynamics of the large-scale gas distribution. Observations of the Sunyaev-Zeldovich effect, which measures the thermal state of the intracluster and intragroup medium through the distortion of the cosmic microwave background spectrum, are beginning to trace the effects of AGN feedback on the gas distribution around massive galaxies and clusters, and future observations with next-generation microwave surveys will extend this capability to higher redshifts and lower mass systems. The cumulative picture that emerges from the study of TON 618 is one of an object that sits at the intersection of many of the most important themes in modern astrophysics: the formation and growth of supermassive black holes, the coevolution of black holes and galaxies, the physics of accretion and relativistic outflows, the structure and evolution of the cosmic web, the nature of space-time in the strong field regime of general relativity, and the thermodynamics and information theory of black holes. Each of these themes is a major area of research in its own right, with its own history, its own open questions, and its own trajectory of future investigation, and they are connected to each other through the physical processes that link the smaller scales, the event horizon of the black hole, to the larger scales, the distribution of matter across the observable universe. The fact that a single object, identified more than 6 decades ago as a faint radio source in a catalogue compiled at a small observatory, can serve as a focal point for so many interconnected areas of science, is itself a testament to the richness and coherence of the physical universe and to the power of the scientific methods that have been developed to explore it. TON 618 is not merely a superlative, not merely the most massive or the most luminous, though it is among the contenders for both titles. It is a concrete manifestation of the extreme conditions that arise naturally in a universe governed by gravity, thermodynamics, and the interactions of matter and radiation over billions of years. Its study has contributed to our understanding of how the universe works, and it will continue to do so as new observational capabilities, from the James Webb Space Telescope to LISA to the next generation of ground-based extremely large telescopes, open new windows onto the most powerful phenomena in the cosmos. The knowledge gained from objects like TON 618 is cumulative, incremental, and provisional, as all scientific knowledge is, but it represents the best current understanding of processes and structures that, for all their remoteness and unfamiliarity, are part of the same physical reality in which all observers and all matter exist.